The topic of today's lecture is problem decomposition and recursion. As we had mentioned in the first class, that for every problem you need to have a mechanism to solve the problem. To solve the problem means that given an abstract definition of the problem in a language like English, we would somehow have to decompose or convert the problem into a sequence of steps, because unless we convert it into a sequence of steps, we cannot solve it on the computer. Secondly, we also saw that when we solve the problem, there are many ways to solve a given problem, and before going into one algorithm directly, we need to look at alternative ways to solve the problem and have and examine each of these alternatives to find out the best possible choice. Today we will discuss the issue of problem decomposition by induction, which is one of the most well studied mechanisms and possibly one of the most well used mechanisms to solve problems at the first level. That is, given a problem decomposition means that given a problem, we break up the problem into sub-problems. So you are given a problem P1 and you break it up into sub-problems S1, S2, S3 and so on up to Sk, and solve these sub-problems. Now each of these sub-problems, when solved, will give a solution back. Result 1, result 2, result 3 and result 4, k say. So given a problem, we break it up into sub-problems, and these sub-problems provide us with results R1, R2, R3 and so on, and the main problem then recomposes or reconstitutes the actual solution to the problem based on the solutions obtained from its sub-problems. That is, you have two phases. One is the phase of decomposition of a problem into simpler sub-problems, and second is recomposition of the solutions of the simpler sub-problems to obtain the solution to the original problem. This is a technique which is used widely to solve a number of problems. It is also easy to conceive of solutions to problems using problem decomposition, because it often brings you the issue of inductive problem solving, in which you solve a problem inductively and use the inductive principle to prove the correctness of your solution. Now, instead of going into the formal mechanisms of problem decomposition and recomposition, our attempt will be to understand how to do it for a large class of problems and how to solve in various problems using this technique. And once we know how to do it and how to do it in a wide sense, so that it is able to capture a set of solutions instead of a single solution, then we will see how, given a problem, we first get the initial solution by problem decomposition, and then we refine the solution to obtain the final algorithm by a process of data structuring. So programming methodology or algorithm design will consist of generating an initial solution by a mechanism of problem decomposition, and then a mechanism of refinement of this initial solution to the final algorithm, which will include the definition of data structures. So we will first take some time to study problem decomposition. We will study it through examples first, and then generalize and synthesize our ideas and try to bring out a methodology to solve problems or to write out good programs in general. So first, our objective is to go through some examples, understand what problem decomposition is about. Here I would like to stress that please do not get yourself biased with a programming language when you do problem decomposition. Problem decomposition is independent of a programming language. Programming comes in at a later stage. You program the solution in a particular language. That language may provide you facilities for doing problem decomposition and recomposition, and you may use those facilities. But the technique of this decomposition and recomposition should be independent of the language in which you are writing the program. So we will try to find out what is meant by that and get a flavor of that. It is very difficult to formalize it at this stage. So we will do it through a sequence of examples. And the first example that we will pick is a problem that we have solved before. This is the problem to find out the factorial of n factorial or n factorial. And we know that to solve n factorial we had written out a recursive program which was looking like this. We have done this program before. We declared an integer and we wrote a variant of this program. We said that if n is equal to 1, val is equal to 1. Otherwise, val is equal to n into fact of n minus 1. And then we return the value of val as the value of this function. This was what we did. Now let us have a look at the structure of this definition. Firstly, it is an inductive definition because fact, in fact, you are calling fact again, but you are obviously calling it with a smaller value of n. If you had called it with a larger value of n, this program would never have terminated. So what did we do with the factorial program? If you look at it in a more mathematical setting, there are two aspects. One is there is an argument n, and there are two conditions. If something happens, we know, otherwise something. Now this condition, here there is no recursion in this condition, whereas here we have the recursive condition. This in all inductive rules are called the base condition. Because in an inductive definition, if you do not have a basis, the inductive definition will not be valid. So you must have a basis condition. This is also called the recursion breaking rule when you look at it from a recursive point of view. And this is called the recursive or inductive condition. Now when you have factorial, so what is the decomposition look like? There are two parts. One is the basis part, which says n equal to 1 results in value is equal to 1. There is no recursion. The second is the inductive part or the recursive part. The condition here is n is greater than 1. And what happens here? Here, if we look back at this, val is equal to n into fact of n minus 1, what we did was we first decomposed the problem into a single subproblem and solved the single subproblem fact of n minus 1. Now this subproblem had n minus 1, which was less, following the inductive principle. If this is true, if you can solve this and you can obtain the solution from a solution of this, then you have obtained a solution for this, provided you have got a basis condition. So, suppose we had taken x equal to fact of n minus 1. This was the problem decomposition, the only and the simplest problem decomposition that we did. And how did we recompose the problem? We recomposed the problem saying val is equal to multiply n with x. So, in the inductive part, there is a basis part to a problem, to a decomposition or to an inductive definition, and there is an inductive part or a recursive part, in which there are two phases, as I mentioned before. One is the decomposition phase, the other is the recomposition phase. That is, looking at the solution of the problem, you obtain a solution of the original problem. So, given a solution of the sub problems, you obtain a solution of the original problem. We will go through such examples in details to understand simple things first, and then we will be able to handle more complex things in a more comfortable fashion. So, given 5, the basis condition does not, these conditions are mutually exclusive, these conditions cannot overlap, these conditions have to be mutually exclusive. So, only one of the conditions will hold. So, based on the condition which holds here, you break it up. This is a diagrammatic representation of what we are going to do. The argument is passed through this. Then here this condition holds, the problem is solved. Once the problem is solved, this value is returned. And here 1 is returned. That returns the value of x at 2, which does 2 into 1 and returns 2. This does 3 into 2 and returns 6. This returns 24 and this returns 120. So, there is a sequence of decomposition, returning, and some recomposition occurs here back. So, at a node, two things occur. One is decomposition and one is recomposition. So, we can look at such problem solving mechanisms in two ways. One is a decomposition phase and a recomposition phase. Though in this particular example we have gone from a program back to its original solution, slowly we shall learn how to solve problems this way first before going into the final algorithm. So, this is a simple case in which one single subproblem was taken into account. Now, let us take another problem. We will take another problem for which the problem itself is defined by the inductive definition. We know that fib takes an argument n, and we have got a basis condition or a base condition as n is less than equal to 1, and we say val equal to 0. Let us say this is our condition. Sorry, val equal to 0 if n is equal to 1, if n is less than equal to 0, and we have got two basis conditions, and when n is equal to 1, val is equal to 1. Okay. These are our two base conditions. And what is the inductive condition? The condition is n is greater than 1, and in order to solve the Fibonacci number problem, you have to obtain Fn, it is Fn minus 1 plus Fn minus 2. So, we solve fib of n minus 1, which is one subproblem. We have to solve and get the solution in, say, x. In y, we solve fib of n minus 2. These are our two decomposed subproblems, and we recompose our subproblem by the addition operation x plus y. This is the complete definition of the Fibonacci number problem. So, these are our two basis conditions. Now, we have got a problem decomposed into two subproblems, and this is the recomposition. So, how will it look like in a diagram? Again, if we draw up, say, 5, now we have got two subproblems, and these two subproblems are actually independent subproblems. They are not dependent on each other. When you look at it from the problem solving point of view, no efficiency, nothing, just whether it gives the correct solution or not, they are absolutely independent subproblems. So, you have to solve 4 and you have to solve 3. Now, to solve 4, you have to solve 3 and 2. To solve this 3, you have to solve 2 and 1. To solve this one, again you have to solve 2 and 1. To solve this 2, you have to solve 1 and 0. To solve this, again you have to solve 1 and 0. This is the complete decomposition rule. Well, you can see there are commonalities here, and what we will do about them we will discuss later on. But looking at the inductive definition, we just open up the whole thing and see what this induction, this is the decomposition tree. Okay, this is the decomposition tree. This decomposition tree was a simple straight line in the case of permutation problems, and this structure has got two children in the case of Fibonacci number problem. And here, now how do the values get returned? Oh, I am sorry, I have missed out something here. this 2. So this returns 1, this returns 0. To solve this, I need to get a value from this. So what is the recomposition from here? It's an addition, 1 plus 0. This one returns 1. Here 1 plus 1, this returns 2. Now to obtain a solution for this will return something 1, this will return 0. So let us draw up all the return links 1, 0, 1, 1, 1. This returns 3, this returns 2, and this returns 5. So the decomposition and each of the subproblems returns to the original problem the solution, and the solution is recomposed, and then this one again returns it back. This is the way the whole thing goes. All right. So this is a decomposition of the. How we will convert each of them into a program, we will see later on. But this is the way in which the problem is decomposed, and this is the way in which the solution is formed. We shall come back to each of them to see how we will write a program. Though we started from problems in which the program can directly be written, but we will now slowly move on to some different problems for which the decomposition itself is more important than writing out the program. The next problem we will take is one of the most well-known problems. Many of you may have done it before. It is also called the Tower of If you do not know the story, I will tell it to you offline. It is said that suppose there is a peg and there are 3 such pegs. We call them A, B, and C. And suppose I tell you that there are discs, obviously with a hole so that it moves into this peg, and the cross sectional view of this disc will be like this. And if I give you one disc and ask you that how will you place this disc onto this, the only move that you are allowed to do is you can move a disc from one peg to another. So moving one disc from A to B is no problem. You just take it out from here and put it in here. So moving one disc from A to B, the answer is move A to B. But suppose I give you 2 discs with the additional condition that this larger disc, there are 2 discs of different sizes, and here there is a larger disc and there is a smaller disc. The smaller disc is placed on top of the larger disc. Now you are to move both of them to a similar configuration into B, but never in your sequence of moves will you be allowed to place a smaller disc below a larger disc. that is always smaller disks should be above larger disks. Then obviously you cannot place this one here and this one here just above it. So the solution that you will take up is move the peg which is on top. Obviously you can move only the peg which is on top, and you cannot carry together 5 or 6 pegs together. Then you could have solved the problem by just pulling all of them up and putting them down. So you can move them only one by one. So the only solution that you have got is move from A to C, then move from A to B, and then move from C to B. Is that okay? So when you move from A to C, this peg will come here, sorry, this peg will come here, and you will reach a configuration, I am sorry, the colors are, you will get a configuration in which one was here and the smaller one is here. Then the next A to B, so this one will be moved here, and you will get the configuration and the last one C to B, this one will move here, and you will get the required final configuration So now we are going to get the problem a little more involved, get a little more involved into the problem. And say that we have got A, B and C, and we have got 3 disks. Now how do we move all 3 from A to B? With the same rules that no smaller disk can lie above a larger disk, and you have to move only one at a time. So let us try out. We can move this one here, A to C, is this visible? Then we can move out this one here, A to B. It is no use moving this one here, because that you could have done in the first step only. So we reach a configuration. Now we have only one option, moving this here. Or retracing your steps. C to A, sorry, C to B. You could have also moved C to A, but if you move from C to A, it would have not led you anywhere, because if you move from C to A, you would have had to move this. You can move from C to A also, you can move from C to B also. Suppose we take the choice from C to A, let us see. Next, any other? Now the only alternative is to move this one here, B to C. The next alternative, I can move this one here, but then I will not be able to move much, because I will have to move this one back here. Because if I move the smallest one here, so the alternative that I have now at my disposal is A to C. So it seems we have reached somewhere, because now we can move at least C to its position. We have reached somewhere, we have reached a situation where we can move C to its position by a sequence of some trial and error. We went here and there and somehow managed to find a position. Look, no, this is a very crucial position, because this is a position where I know that if I can get to this position, I can solve the problem, isn't it? Because if I move here, then I know the sequence of steps, because 2 disks I can move on top of this. That is, now if I move from A to B, I have done this. But this is very interesting, because at this point I know I can forget about this fellow. All I have to do is move these two here, which is similar to moving 2 disks from one peg to another, something which we have solved before, isn't it? Because now I need not touch this one. So I have just to move these 2 disks back here, for which I have done that problem before. I can use the problem of induction, and I can straight away write out that to solve this one I will move this one here, this one, next one here, and this one back. So the sequence of steps is C to A, C to B, and A to B. I hope I do not have to write down these diagrammatically, it is quite clear. So now we have taken 1, 2, 3, 4, 5, 6, 7, 8, 9 steps to reach this position. If we go back and analyze further and come back and see what we have done, then we will see that by a sequence of these 5 steps we have reached this position. Actually we moved in a random fashion, somehow just we moved something here and there, whatever we felt. But once we reached this position, we knew that we have solved the problem. Now let us go back and see, is this the least number of steps in which I can do this? At least from here to here, this is the least number of steps. Because if this were not the least number of steps, then 2 disks movement problem I could have solved in less than 3 steps. We saw that moving 2 disks we could not solve in less than 3 steps. So we can go back and see whether we can solve this problem faster. And to solve this problem faster, we have to have a look at what we have done. We have actually moved, we had 3 disks here, isn't it? We have actually moved these 2 disks here. That is all what we have done. We have moved the top 2 disks here, nothing else. Now, and we have required 1, 2, 3, 4, 5 steps. But to move 2 disks from one peg to another, we can easily do it in 3 steps. So this one, we can revise and improve our solution up to here. These 6 steps that we have taken, these 5 steps that we have taken can be improved. And the improvement is, to bring it from here to here, I need to bring this down, this up, and this back. So all I need to do was A to B instead of this A to C which we did. A to C now, and B to C. Follow it up with this one and these. A to B, C to A, C to B, and A to B. So, in 7 steps we can solve the problem for 3 disks. So, that is fairly interesting that we have solved it in 7 steps, and I will leave it to you to try your hearts out to solve this in less than 7 steps. You would have to lift 2 disks, but you can sit down and prove it, and since it is just a case of 3 disks, you can prove it by exhaustive enumeration. There is no problem. You can try out all possible combinations of 7 steps and see this is the only one which reaches the solution. But the next question is, if I give it, what have we understood from this problem? We have understood that to solve the 3 disk problem, we have used the solution of the 2 disk problem. And how have we used the solution of the 2 disk problem? To solve the 3 disk problem from A to B, we have solved the 2 disk problem from A to C because the larger disk need not be touched. Then we have moved the largest disk from A to B, and then we have moved, and then again we have solved the 2 disk problem from C to B. So we can recollect what we have done about the 3 disk problem. This was the original position, A, B, C. So to solve the Tower of Hanoi 3 disk problem, we obtained a configuration first like this. Look, now we are not looking at it element by element. Slowly we are looking at it sub-problem by sub-problem. A, we solved this. Then the next step that we did was this. And the next step that we did was move these to here. So we actually solved it in 3 steps, of which 2 of them were inductive steps and 1 of them is a base step, because moving this from here to here is the problem of moving a single disk, and moving these 2 from here to here is the problem of moving 2 disks. So to solve the problem of Tower of Hanoi with 3 disks from A to B using C, we solve the problem of 2 disks from A to C using B. We solve the problem of 1 disk from A to B using C, and we solve the problem of 2 disks from C to B using A. Is that understood? So now to solve the 3 disk problem, now in order to solve the 4 disk problem, what do we do? How do we now solve the 4 disk problem? Do we start like this, random fashion? I think we have learned something here. To solve the 4-disk problem from here, we can solve the 3-disk problem. Then we can solve the 1-disk problem. And then again we can solve back the 3-disk problem. And the number of steps that we will take will be 7 plus 1 plus 7. So we will take 15 steps to solve this problem. Okay? I leave it to you to think over that this is the minimum number of steps to solve the Tower of Hanoi's problem for 3 pegs. So now generalizing this to n is very easy. If this is n, this is n minus 1, this is 1, and this is n minus 1. So on the basis of this, we have now got at least a solution. Proof of minimality of number of steps is left to you. At least we have got a solution to solve the Tower of Hanoi's problem. In the next class, we shall come back to this solution and study what is meant by the recomposition. Here we will see how we write it down in form of decomposition and recomposition, and then we will see how we convert it into a program.